my people. How are you doing? I hope your day has been going on well. Yes, in continuation of our lecture on chemistry 235, basic organic chemistry. This time around, we'll be discussing on the structure of an atom. In our previous lesson, we discussed the determination of the structures of organic compounds. Now, we want to talk about structure of an atom. This is important because we need to understand what an atom is so that we're able to understand the reactions of organic compounds. And at the end of this lecture, we are expected to be able to describe the structure of an atom, define atomic number, define atomic mass or mass number as you like, describe isotope, explain the distribution of electron in an atom, describe the atomic shell and atomic orbiter, and also be able to describe electronic configuration of atoms. The structure of an atom, to start with. As we all know from our O-level elementary chemistry, atom is the simplest unit of the matter. The atom itself has its own structure. An atom consists of a tiny dense nucleus surrounded by electron. You have the nucleus, which is surrounded by electron. The electrons are spread throughout relatively large volume of space around the nucleus. Okay, the electron is around the nucleus. The nucleus contains positively charged proton and neutral atoms. While the electron is revolving around the nucleus itself contains protons, which are positively charged, and neutrons, which are neutral. While the nucleus is positively charged, electrons are negatively charged. The nucleus is positively charged because of the presence of the protons, which are positive charged, and the electrons are negatively charged. As you can see here, the structure of an atom is depicted here. This circle indicates the space in which electrons revolve around the nucleus. The nucleus. You can see this one, the nucleus. We have the first circle represent the first electron space, which is closer to the nucleus, and so on as you go out. These circles are called shells, and their name will come about their names later on. Protons and neutrons have approximately the same mass. Protons and neutrons have approximately the same mass. Protons and neutrons are about 1,800 times more massive than electrons. In other words, protons and neutrons are more heavier than electrons. So electrons, the mass of electrons are negligible. So they don't count when you are talking about atomic mass. We are coming to that. This means that most of the mass of an atom is in its nucleus, because the nucleus is housing the proton and the neutron. However, most of the volume of an atom, the volume is occupied by its electrons. Okay, as you can see from the previous slide, okay, this volume of the atom is occupied by electron, and electrons are involved in chemical bonds of atoms. So our focus will be on the electrons. Atomic number. The atomic number of an atom equals the number of protons in its nucleus. Okay? The atomic number is also the number of electrons that surround the nucleus of a neutron atom. So we are talking about atomic number of an atom. It is the same as the number of protons in the nucleus or the number of electrons around the nucleus. For instance, the atomic number of carbon is 6, which means that a neutral carbon atom has 6 protons and 6 electrons. Because the number of protons in an atom does not change, the atomic number of a particular element is always the same. All carbon atoms have an atomic number of 6. Mass number, or atomic mass, if you like. The atomic mass of an atom is the sum of its protons and the neutrons. Since protons and neutrons make up the mass of the atom and they reside in the nucleus, so the mass number of an atom is the summation of the protons, the number of protons, and the number of neutrons. Now, not all carbon atoms have the same mass number, because even though they all have the same number of protons, they do not all have the same number of neutrons. In other words, we have different carbon atoms. In fact, we have 3 of them: carbon 12, carbon 13, and carbon 14. Okay, this is as a result of the number of neutrons in the nucleus. They are not the same. Here it is explained here. For example, 98.89% of naturally occurring carbon atoms have 6 neutrons. 98.89% have 6 neutrons, giving them a mass number of 12. That they have 6 neutrons, 6 protons, making 12. However, 1.11% have 7 neutrons, giving them a mass number of 13. Okay, carbon 12, carbon 13. These 2 different kinds of carbon atoms, carbon 12 and carbon 13, are called isotopes. Isotopes have the same atomic number, the same number of protons, but different mass numbers because they have different number of neutrons. So we now know what isotopes means. Okay, they are atoms of the same element having the same atomic number but different mass number. The chemical properties of isotopes of a given element are nearly identical. Naturally occurring carbon also contains a trace amount of carbon 14, which has 6 protons and 8 neutrons, carbon 14. This isotope of carbon is radioactive, decaying with a half-life of 5,730 years. That is carbon 14. It's an isotope of carbon and is radioactive. Atomic weight. The atomic weight of a naturally occurring element is the average weighted mass of its atoms. Because an atomic mass unit is defined as exactly 1/12 of the mass of carbon 12. Okay, here the atomic mass of carbon 12 is 12 atomic mass unit. Atomic mass of carbon 13 is 30.0034 atomic mass unit. So the atomic mass of carbon as an element or an atom is the average or cumulative average of the atomic mass of carbon 12 and carbon 13. That's why you have this relation or calculation rather. Therefore, the atomic weight of carbon is 12.011 AMU, which is obtained by multiplying the percentage number of carbon 12 with the mass and the percentage mass of carbon 13 with the mass to give us the average of 12.011, which we normally approximate as 12. The molecular weight is the sum of the atomic weight of all the atoms in the molecule. That's molecular weight. We'll talk about molecular weight in our previous lesson. So we just leave this as it is now. Now, this is the structure of carbon atom as we have described. This is the nucleus housing the protons and the neutrons. And these are the electrons around the nucleus. Okay? Okay, the electrons, proton, and neutrons. And these are the shell. In other words, carbon as an atom has 2 shells. Okay? Now, we talk about distribution of electrons in an atom. How are electrons distributed? Electrons are moving continuously, as depicted in this picture. These eccentric circles indicate that the electrons are in constant motion. They are not static. They are in a continuous motion. And like anything that moves, they have kinetic energy. The energy is what contains the attractive force of the positively charged protons that would otherwise pull the negative charged electron into the nucleus. You remember we said the protons are not positively charged, while the electron are negatively charged. Ordinarily, we expect an attraction between the opposite charges, positive and negative. And since the protons are in the nucleus, they are static, it stay there permanently. It means that the proton will be pulling the electron toward itself, be attracting it toward itself. Because the electrons are in constant motion, okay, protons was not, I mean, the protons are not able to attract the electrons towards themselves. Electrons were perceived to be particles, okay, infinitesimal planet, that is, very small planets orbiting the nucleus of an atom. But in 1924, a French physicist named Louis de Broglie, this gentleman, showed that electrons also have wave-like properties. And he proved this by combining a formula developed by Einstein, this gentleman, that relates mass and energy with a formula developed by Planck, relating frequency and energy. Okay, so this gentleman made us understand atom and the structure better. Let's continue. Distribution of electrons in an atom. The realization that electrons have wave-like properties, okay, encouraged physicists to propose a mathematical concept known as quantum mechanics for atomic structure. Now, the version of quantum mechanics most useful to chemists was proposed by Erwin Schrödinger in 1936. So this is another gentleman that contributed to the structure of atom, Erwin Schrödinger. According to Schrödinger, the behavior of each electron in an atom or a molecule can be described by a wave equation. The solutions to the Schrödinger equation are called wave functions or orbitals, and this is where orbitals come in. Okay, these orbitals or wave functions tell us the energy of the electron and the volume of space around the nucleus where an electron is most likely to be found. In fact, orbitals have been defined as space of highest probability where you can find an electron. According to quantum mechanics, the electrons in an atom can be thought of as occupying a set of concentric shells that surround the nucleus as you have it here. This picture of the nucleus brought out here. This is the nucleus here, as you can see it here, but it has been enlarged here to show you that you have proton and neutron. The first shell is the one closest to the nucleus. The second shell lies further from the nucleus and even further out lie the third and higher numbered shells. Okay, as already displayed here, that you have the shell in the middle here. The shell that is closer to the nucleus is the first shell. The one that's next to it is second shell, and so on and so forth. Each shell contains subshells known as atomic orbitals. In each shell, you have subshell known as atomic orbitals. Each atomic orbital has a characteristic shape and energy. Each atomic orbital occupies a characteristic volume of space, which is predicted by the Schrödinger equation. An important point to remember is that the closer the atomic orbital is to the nucleus, the lower is its energy. Meaning that the shell number one, which is closer to the nucleus, or closest to the nucleus, has the lowest energy. The second shell, which is a bit far away from the nucleus, is of higher energy, and energy increases as you move away from the nucleus. The electron shell may be thought of as an orbit, okay, followed by electrons around an atom's nucleus. Okay, this is what we have explained before. The closest shell to the nucleus is called 1 shell or K shell, followed by the 2 shell, L shell, then the 3 shell, M shell, and so on further and further from the nucleus. The shells correspond to the principal quantum number. The shells are numbered as 1, 2, 3, 4, with 1 being the shell closer to the nucleus, and so on like that. This N is what is known as principal quantum numbers. We are coming to that in a nutshell. The shells are also labeled alphabetically as K, L, M, and so on. Now, quantum numbers. There are a set of numbers used to describe the position and energy of the electron in an atom. These are called quantum numbers. And we have 4 different quantum numbers that are used to describe an electron in an atom. These are the principal quantum numbers, which are the symbol N. We have azimuthal or angular quantum numbers, L, magnetic quantum numbers, M, superscript L, or subscript rather, subscript L, and you have the spin quantum numbers, which has the symbol M with subscript S. So these are the 4 principal quantum numbers that are used to describe the position of an electron in an atom. The principal quantum numbers is denoted by the symbol N, and it designates the principal electron shell of the atom. It tells you the position, the shell in which the electron is located. The value of the principal quantum number can be any integer with a positive value that is equal to or greater than 1. In other words, N, the principal quantum number, start from 1, 2, and so on like that. N can never be 0, and it can never be negative. The value N is equal to 1 denotes the innermost electron shell of an atom, which corresponds to the lowest energy state or the ground state of an electron. Then the second one, the azimuthal or angular quantum numbers, L. The azimuthal or orbital angular momentum quantum number describes the shape of a given orbiter. Remember, we have orbiter in the shell. So azimuthal describes the shape of the orbiter. It is denoted by the symbol L, and its value is equal to the total number of angular nodes in the orbiter. A value of the azimuthal quantum number can indicate either an S, P, D, or F subshell or orbiter, which vary in shapes. They have different shapes, S, P, D, or F. This value depends on and is capped by the value of the principal quantum number. The value of the azimuthal quantum number ranges between 0 and n minus 1. Okay, that means if n is 1, L will be 0. If n is 2, L will be 1, and so n minus 1. For example, if n is 3, the azimuthal quantum number can take on the following values: minus 0, take on the values 0, 1, and 2. When L is 0, the resulting subshell is an S orbiter. Similarly, when L is 1 and L is 2, the resulting subshell are P and D orbiters, respectively. Therefore, when N is 3, the 3 possible subshells are 3S, 3P, and 3D. In another example, where the value of N is 5, the possible value of L are 0, 1, 2, 3, and 4. If L is 3, then there are a total of 3 angular nodes in the atom. This figure represents what we mean by azimuthal angular quantum numbers, or L. These are possible L we can find in an atom. When N is 1, okay, L is 0, we have 1s. Because if L is 0, we have the S orbiter, and the shell is 1. That's why we have 1s. When N is 2, The shell is 2 and L is 1. That is 0 and 1. That's why you have 2s, 2p. When n is 3, we have 3s, 3p, 3d. When n is 4, 4s, 4p, 4d, 4f. When n is 5, we have 5s, 5p, 5d, 5f, and so on and so forth. Now, the third one, magnetic quantum number. Magnetic quantum number determines 1, the total number of orbitals in a subshell. 2, the orientation of these orbitals. It will determine the total number of orbitals and their orientation. Magnetic quantum number is denoted by M subscript L. This number yields the projection of the angular momentum corresponding to the orbital along a given axis. For a given value of L, that is azimuthal quantum number, the value of ML ranges between the interval minus L to plus L. This indicates that the value of magnetic quantum number depends on the value of principal quantum number. For example, if n is 4 and L is 3 in an atom, the possible values of the magnetic quantum number are minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Now, this represents the shape of orbitals, okay, as quantum numbers. The one you are up here is the S shell, which is spherical in nature. Then you have the P shell. The P shell is like a dumbbell, as you can see here. The S orbital has no subunit. That's why it just is a single spherical or like a ball, if you like. But P has 3 subshells. That's why you have PX, PZ, and PY. Then you have the D orbital. The D orbital has 5 suborbitals. As you can see here, you have dx square y square, dxz, dz square, dyz, and dxy. These are the 5 suborbitals of D. Then you have F orbital. F orbital has 7 suborbitals, as shown here. Now, for instance, if n is 4 and L is 3 in an atom, the possible values of the magnetic quantum number are minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. The total number of orbitals in a given subshell is a function of the L value of that orbital. It is given by the formula 2L plus 1. For example, the 3D subshell, N is equal to 3, L is equal to 2. It contains 5 orbitals. Okay, as you can see with the formula 2 times 2 plus 1. Each orbital can accommodate 2 electrons. Therefore, the 3D subshell can hold a total of 10 electrons. 3D subshell, which has 5 suborbitals, can hold a total of 10 electrons because each suborbital can hold 2 electrons. This is summarized in this table here. Azimuthal quantum number. Okay, if it is 0, you have S subshell. Then corresponding number of orbitals, 2 times 0 plus 1 is equal to 1. That is the orbital there. Possible value of M is 0. If N is 1, okay, you have the P subshell. That is 2 times 1 plus 1 is equal to 3. You have minus 1, 0, and 1. If it is 2, you have D subshell. 2 times 2 plus 1, 5. Minus 2, minus 1, 0, 1, and 2. And F subshell, you have 7 suborbitals in F. Then the fourth quantum number is this electron spin quantum number. This is dependent on the values of N, L, and ML. Okay, electron spin cannot be determined by the principal quantum number or the asymmetrical quantum number or the magnetic quantum number. It cannot be determined on its own. The value of this number gives insight into the direction in which the electron is spinning and is denoted by the symbol m subscript s. In other words, the electron spin quantum number will tell you in which direction the electron is spinning. Is it spinning clockwise or spinning anti-clockwise? That is what spin quantum number tells us. And the possible values of the electron spin quantum number are plus half or minus half. If magnetic spin quantum number is plus half, is positive, it means the electron is spinning upward or clockwise. You can see spinning up, spin up, and is denoted by the arrow going up. And if it is negative, minus half, it means that it is spinning in the opposite direction, spinning down, as denoted by this symbol arrow. The value of the electron spin quantum numbers determine whether the atom in question has the ability to produce a magnetic field. That is the importance of electron spin quantum number. It will tell you whether it has a magnetic field or not. And the value of ms can be generalized to plus or minus half. It's either it's plus half or minus half. That's why it's known as plus or minus half. It's either spinning up plus half or spinning down minus half. Now, this table also summarizes the the quantum numbers of electron. But it is important to note that it is impossible for two electrons of the same atom to have exactly the same quantum states or exactly the same values for the set of quantum numbers. It's not possible. They have different, no two electrons in an atom can have the same set of quantum numbers. And here you have the table here. You have the principal quantum numbers, n, which is electron shell. N is equal to or greater than 1. Then you have the azimuthal quantum number, L, subshells, S0, the s orbital, L is 0, p orbital, L is 1, and so on. And azimuthal quantum number is given by n minus 1. Okay? Magnetic quantum number, ML. This is total number and orientation of orbitals. And is given by L greater than or equals to ML or greater than or equals to minus L. Then you have the electron spin quantum number, which is the direction of electron spin. And ms is either plus or minus half. Okay? Now, electronic configuration. Electronic configuration. The ground state electronic configuration of an atom describes the orbitals occupied by the atom's electrons when they are all in the available orbitals with the lowest energy. In other words, the electronic configuration of an atom describes the arrangement of electrons in the atom. Simply put, just like that. If energy is applied to an atom in the ground state, one or more electrons can jump into a higher energy orbital. The atom then would be in an excited state of electronic configuration. When you apply energy and an electron gain energy and jump up, then we say the atom has become excited. So now it's in an excited state. Now, these principles are used to determine which orbital an electron will occupy in an atom. One of them is the off-bound principle. Off-bound. The off-bound principle tells us the first thing we need to know to be able to assign electron to the various atomic orbitals. According to this principle, an electron always goes into the available orbital with the lowest energy. That means when you are filling up an atom with electron, you first of all fill the orbital with the lowest energy, before you feel the one with the next higher energy. The relative energies of the atomic orbitals are as follows. 1s atomic orbital is closer to the nucleus. It is lower in energy than 2s atomic orbital. 2s atomic orbital is also lower in energy than and closer to the nucleus than the 3s atomic orbital. In other words, when you are filling the atom with electrons, you first of all go to the 1s, which is closer to the nucleus and of lowest energy. When it is filled up, you now go to 2s. When 2s is filled up, you now go to 3s, and so on like that. Comparing atomic orbitals in the same shell, we see that an s atomic orbital is lower in energy than a p atomic orbital. In other words, in the same shell, you first of all fill s orbital before you go to p orbital. The s orbital has to be filled up before you can start filling up the p orbital. A p orbital, a p atomic orbital is lower in energy than a d atomic orbital. Okay, so you fill up p atomic orbital before you go off to d atomic orbital. And this figure illustrates how you fill up orbitals with electron. For example, if you follow this chart, you say first of all you fill 1s, then you go to 2s. After 2s, you go to 2p. After 2p, you go to 3s, 3p, 4s, 3d, and so on like that. Or if you use this chart, this has been arranged. This one here indicates the first shell. And in the first shell, only s orbital is available. Okay? So it's when you fill off the first shell, the s orbital, before you go to the next shell, which is 2. In the second shell, you have 2s and 2p. In the third shell, you have 3s, 3p, and 3d. In the fourth shell, you have 4s, 4p, 4d, 4f, and so on like that. Now, you can see this red arrow. This red arrow indicates the direction how you feel electron. Okay? Because you can assume that the energy of the orbitals increases from the tail to the head. So, and you feel electron from the tail to the head. So, when you are feeling electron, you first of all feel 1s. After 1s, you go to 2s. After 2s, you go to 2p, 3s. After 3s, you go to 3p, 4s. Before you now come to 3d. Okay, 3d is an higher energy than 4s. That's why you have to fill off 4s before you go to 3d, and so on. When you are filling up electron and you follow this chart, you'll be able to write electronic configuration of your atom seamlessly. So don't forget, this chart will be helpful for you when you ask to write an electronic configuration of an atom. Another principle that guides us in filling up electron is the Pauli exclusion principle. This states that no more than 2 electrons can occupy each atomic orbital. Already we know this one. And the 2 electrons must be of opposite spin. Now that if you have 2 electrons in an orbital, they will not spin in the same direction. They'll be spinning in an opposite direction. From the first 2 rules, that is overall principle and Pauli exclusion principle, we can assign electrons to atomic orbitals of 4 atoms that contain 1, 2, 3, 4, or 5 electrons. Okay? Then the third one is the Ohm's rule. This states that when there are degenerate orbitals, degenerate orbital means orbitals that are of the same energy level. For example, 2p. In 2p, you have 3 suborbitals. They are in the same shell, or the same, yes, they are of the same energy level. These are degenerate orbitals. 2 or more orbitals with the same energy, yes. An electron will occupy an empty orbital before it will pair up with another electron. That is, for example, if you have a 3p orbital and you have 4, yes, you have 3 electrons. You have 2p orbitals and 3 electrons going into 3p orbitals. The electron will go into each of the orbitals before they start pairing up. Each orbital will have to be occupied by an electron, one each. Not that two of the electrons will go to one orbital and one electron will go to another orbital and the other orbital will be empty. No. The electron will be shared equally among the three orbitals. But if you now have additional orbital, then they start pairing up according to the energy level of the orbital. This is so because electron repulsion is minimized. Okay, you reduce electron repulsion. The sixth electron of a carbon atom therefore goes into an empty 2p atomic orbital rather than pairing up with the electron already occupying a 2p atomic orbital. The seventh electron of a nitrogen atom goes into an empty 2p atomic orbital. The eighth electron of an oxygen atom pairs up with an electron occupying a 2p atomic orbital rather than going to a higher energy 3s orbital. Using these three rules, the locations of the electrons in the remaining elements can be assigned. And examples have been given for us here from hydrogen to sodium, how we can write the electronic configuration. This is for hydrogen, the atomic number is 1. And so the electron is going to 1s orbital. For helium, the atomic number is 2. The 2 electrons are occupied by 1s orbital. So if you want to write the electron configuration for hydrogen, for example, we said 1s upper script 1. For helium, we say 1s upper script 2. Lithium, which is 3 atomic number, it is 1s2, 2s1. Beryllium, which has 4 electrons, is 2s2, 1s2, 2s2. Boron, which has atomic number of 5, the electron configuration goes 1s2, 2s2, 2p1. Carbon, which has 6 electrons, the electron configuration goes as 1s2, 2s2, 2p2. But since you have 3 p orbitals, these 2 electrons go to 2px and 2py. But if you want to write the electron configuration, we said 2p2. But we know that they go into different orbitals in 2p. Similarly for nitrogen, it is 1s2, 2s2, 2p3. For oxygen, 1s2, 2s2, 2p4. Okay? For fluorine, it is 1s2, 2s2, 2p5. And for neon, which has atomic number of 10, it is 1s2, 2s2, 2p6. You can see that for neon, all the p orbitals are occupied with electrons. And you can see how the electrons are shared from boron to neon. You first of all arrange the electrons singly before we start pairing them up until we get to neon. And for sodium, which has atomic number of 11, it is 1s2, 2s2, 2p6, 3s1. And so this is how we write electron configuration and so on like that. In summary, so far we have discussed, we have learned in this lecture that atom consists of tiny dense nucleus surrounded by electrons. The electrons are spread throughout a relatively large volume of space around the nucleus. The nucleus contains positively charged protons and neutral neutrons. Nucleus is positively charged. Electrons are negatively charged. The atomic number of an atom equals the number of protons in its nucleus or number of electrons that surround the nucleus of a neutral atom. The mass number or atomic mass of an atom is the sum of its protons and neutrons. Isotopes are 2 or more atoms of the same element having the same atomic number but different mass numbers because of different number of neutrons. Atoms consist of electron shells, which are spaces around the nucleus. Each shell comprises of orbitals. Okay, electrons have wave-like properties defined by a mathematical concept known as quantum mechanics. Electrons in an atom occupy a set of concentric shells that surround the nucleus. We have also described the atomic shell and atomic orbital. Okay, the shells correspond to the principal quantum numbers n is equal to 1, 2, 3, 4, and so on, which are also labeled alphabetically with the letter used in the X-ray notation K, L, M, N, and so on. Quantum numbers, principal quantum numbers, azimuthal or angular quantum number, magnetic quantum number, and spin quantum number are used to describe the position and energy of the electron in an atom. Okay, it is not possible for two electrons of the same atomic of the same it is not possible for two electrons of the same atom to have exactly the same values of the set of quantum numbers. The electronic configuration of an atom describes the orbitals occupied by the atom's electrons when they are all in the available orbitals with the lowest energy. The Hofbauer principle, Pauli exclusion principle, and Ohm's rule are the principles used to determine which orbitals electrons occupy. Thank you for today's lecture, and you can use this for further reading. If you want to read more about this lecture, you can consult any of these sources. From there, you'll be able to get more insight into what we have been discussing so far. God bless.